Hello, ladies and gentlemen, and welcome back. We're going to be finishing off the 2009 Euclid contest in this video. So we're going to be up to question number 10, the very last question on the contest. What do we got here? Suppose there are n plates equally spaced around a circular table. Ross wishes to place an identical gift on each of the k plates. This sounds like circular choosing. Sounds like the necklace problem almost. So that no two neighboring plates have a gift. Interesting. So it almost has to alternate, although I guess you can have an empty number in between gifts. Interesting. Let f and k represent the number of ways you can place the gifts. So n plates, k gifts. And you can't have pairs of gifts. For example, n63 equals 2. So it looks like the plates have numbers here. Because, I mean, this second one over here is just a rotation of the first one. Just move everything one to the right, which means this isn't circular combinatorics or the necklace problem, but it looks similar. I wouldn't be surprised if there was a couple of choose notations or binomial coefficients lurking around here, like a p choose q or something. Alright, so with a question 10, it's usually always contained, like, it's one concept that's expanded upon. You know, there's usually an introductory question, then figure out a simple result, then figure out a very big result. You know, that sort of a thing. And the big result, C or D, usually uses the previous parts. But always try 10A. Even if you barely understand what's going on, 10A is usually 1 or 2 marks. Just, you know, can you write out a case of this? Can you understand this? Can you simplify this one expression? It's not really a taxing thing. So, but with 10 being related to a whole concept, I usually read A, B, and C all together. Gives me a little bit of direction. That's all. Just gives me a little bit of direction. Okay. So, A, determine the value of 7, 3. Okay, not too big a deal. Just have 7 of them around. You know, I might be 4 or 5, honestly. I don't think there'll be that many to actually write out. B part, prove that f and k... Oh, here we're slowly getting sort of a formula. F and k is fn minus 1k plus fn minus 2k minus 1. So we can lose a plate and still have the same number of gifts, or we lose 2 plates and have 1 less gift. Okay, now when I read that, I'm not going to get to C right now, but immediate brainstorming are things like the Fibonacci sequence. Because there's a way to sort of... what I'm thinking here is, because the plates are numbered, we get sort of a 1, 2, 3, 4, 5, 6... And we could say no gift, a gift, no gift, a gift, no gift, a gift. You can generate strings like this, and there are ways to view the Fibonacci sequence as strings. And the way you make new strings are you either add on a 0 or you add on a 1, and you get different sums based on certain things. So I'm immediately drawn to that idea that there could be binary strings with Fibonacci. This also looks a little like... sort of properties that these binomial coefficients have. It's not quite the same, but I think it's what makes the Pascal's triangle work out. I think it's the previous one plus... I think this is the... well, you know what, I can work this out. 6, no, let's not say 6. Let's say 4 choose 2 is 6. And if I'm right, then that's 4 choose 1, which is 4 plus... No, my formula decided that would be 4 choose 1, that's 4. And then that would be 3 choose 1, which is 3. Okay, I don't quite have the right formula, but there is a formula like this. Now I'm curious as to what it is. Is it P minus 1Q? Yeah, because the top number is the row number, so it's the previous row. So That would be 3 choose 2 plus 3 choose 1. Yeah. And those are both 3. So, there's something similar to that. It's not quite the same. So, and certainly you wouldn't expect it to be quite the same, because I certainly would want question 10 to be a bit more complicated than fnk is n choose k, and clearly it's not, because 6 choose 3 is not 2. But it's something like that. So it's something like that. It's off. This should be a 1, not a 2, but it's something similar. And so maybe with B we have to do binomials or something like that. And then C part, determine the smallest possible value of n plus k. N plus k, so now I'm thinking maybe there's an expression like this for fnk. Among all possible ordered pairs for which fnk is a positive multiple of 2009. Okay, I don't like that. Positive multiple of 2009. So now I'm thinking multiples of 2009. I'm thinking factoring 2009. I'm thinking a big headache because I'm thinking I'm going to need to get my calculator out and know a couple of multiples of 2009. And we want n greater than or equal to 3, k greater than or equal to 2. I think, yeah, we've got that for just about everything. Okay. So I may need to get my calculator out for C part. But I don't know. Let's ease into this with A. So we've got we want 7, 3. So let's just play around with it. I don't think... Yeah, I think we're going to avoid plates and actually drawing pictures. I mean, you can. I think it's just going to be a bit of a waste of time. And certainly drawing all those circles. So I guess I could do something like no gift, gift, no gift, gift, no gift, gift, no gift. And that would be one of them. And I suppose you could rotate this, but I think it's probably going to be healthy to introduce early on something like since the plates are numbered, we can associate each. They don't give a name to this, like special or accurate or allowed or valid or correct or Rossable or something like that. They don't have a special name for this, right? No. So each, I don't know, permitted or something like that. We can associate each, I guess we'll just say arrangement. Let's spell arrangement right. Also, the pen is not really picking up my writing movements, which is never good. I'll try and write a bit slower. We could say, I could use dots and X's. I think it's probably just going to be easier to use a binary string. So maybe moving closer to that Fibonacci thing. So a binary string would say B1, B2. Or I could go P for plates, G for gifts, or I could say A. I mean, really, I can use anything I want. Where there are K1s and N minus K zeros. And for all I, if BI is 1, then what do I need? I need the ones beside it can't be 1s, so they have to be zeros. And I guess if B1 is 1, then B2... Now the pen is really not liking me. And the last one has to be 0, because that's completing the circle. So 1's here and 7's here. And the other end, so if Bn is 1, Then B1 is 0, and so is Bn minus 1. Alright, so let's get that out of the way. That way I don't have to draw pictures. Okay. Does that actually help me with 7 and 3 gifts? I don't quite think so, but... What to do? I mean, I've really just been putting it off. I think I just have to play around with it. So I'll just imagine I have 4, 5, 6, 7. And I don't know, let's suppose we put a gift here. Well, then there's got to be a gift here and here. Or, sorry, there's got to be no gifts there and there. And then I've got... I could have a gift here, but that forces a gift here. And then I could either have a gift here or a gift here. So that's 2 possibilities. Or I could have no gift. And then I'm forced to have a gift here. So that's another 1. I can't have double 0, because then I'd have 1, 1. So, okay, that's if I have a leading 1. What if I have a leading 0? Well, then I can either have 1, 0, 1, 0, 1, 0. Or I could have 0, 1, 0, 1, 0, 1. So that is a total of 5. Have I missed anything? So, it's important to try and go at this logically. And say, alright, where are my choices? And so now I'm starting to think that we might rely a bit more heavily on binomial notation. But let's sort of write this up a bit more. Okay, so got B1, B2, B3, B4, B5, B6, and B7. If B1 is 1, B2 and B7 are 0. So I've got 1, 0, blank, 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 0. Or I guess B3. I'm going to replace the blanks with the B's. And then at this point I have a choice to make. If B3 equals 1, then B4 is 0, and we get 2 possibilities, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0. Okay. I mean, I'm basically doing what I just worked out on the previous page, but I'm writing it up a little slower. Need to place 2 gifts. It is really not picking up on the subtlety of my handwriting. This is going to be fun for the next... I don't know, what do the 10s usually take me? 40, 50 minutes? 1, 0, 0. There's a 0 at the end, so it's got to be 1, 0, 1. If B1 equals 0, 6 spaces left, 3 gifts, so we must alternate. So we get 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1. Okay. There isn't a way to switch those up, right? There isn't a 0, 1, 0, 0, 1, 0, 1, is there? Oh, no, I guess I did just do that. So, wait. Are there a bunch more that I could have? Yeah, it looks like I can, so... Okay. So it's not we must alternate. Okay, 0, 1, 0. But as soon as I do a 0, 1, then I'm forced to do 0, 1s for the rest of the thing. So I guess we can make blocks of 1 zeros and 0 ones. A 0 1 can't follow a 1, or no, a 1 0 can't follow a 0 1. And I guess this is sort of true. We might... Oh, wrote it backwards again. As I'm doing this one, I'm slowly understanding how these things are put together, and I think that's going to help me for B part and maybe for C part. I think for B part, we're shooting for a formula maybe that we can use. So we either have 3 1 zeros, which gives me 0, 1 0, 1 0, 1 0. Or 2 1 zeros and 1 0 1. So that'll be 0, 1 0, 1 0, 0 1. Or 1 10 and 2 0 1s. Or just 3 0 1s. Which will give me 0, 0, 1, 0, 1, 0, 1. So this is 2 cases plus 1 plus 1 plus 4. This is 4 cases here, so that's 8, right? I haven't miscounted something. 2, 1, and then these ones, yeah. Okay. So I've got 8 cases here. Good, fantastic. I don't think there was a particularly faster way that this could be done. The only thing that I can even sort of think about is, I mentioned briefly the necklace problem. This is if you've got sort of black and white beads and thread them around a necklace. Number of patterns there, and you can sort of get like circle permutations if you know what that is, but now it's circle combinations. It's circular multinomial coefficients. And if you had some knowledge of that, maybe there's something you could work out here, but I really don't think so. I think it'd be more trouble than it's worth. I think this is probably the best way to go. And so 8. And once I get my formula in B, I'm going to test this 8. Now, I'm fairly confident in this 8, especially because I caught that last little mistake that I was making that doesn't just alternate. The reason I caught that, by the way, is I made a similar mistake about a month ago when I was doing review for my finite math class. And that it turned what I thought was a simple review question into a very long question. Things to watch out for. Anyway, but I will come back and test this 8. And if my formula, if I'm more confident in my formula, then I'll believe the 8 if I get it. If I'm doubting my formula, well, I've got a couple examples. I can do the 6-3, and now I've got 7-3, I think. I'm pretty sure I got 7-3, though. I think it's 8. Okay, so I've got that. I've learned a bit. Now B, I want to show something like this. There we go. Now, I've got these binary strings, and I suppose I could do something like, well, if I've got a string of 7 that works, or sorry, just sort of any string, let's just pick one of these guys up here. If it, say, ends in these 2 and I chop it off, well, there's a string that works for 5, which would be, you know, one of these. And that's certainly a way to think about it. Is that the only way? Because that doesn't usually, like, that would give me this nice recursive relationship. And that's how it works when I do things with Fibonacci binary strings. But that doesn't give me a formula. That just gives me a recursion. Which is fine for B, but I get the sense that in C, I'm probably going to, because we want multiples of 2009, I think it'd be really nice if we had like a formula, and possibly a formula that didn't have addition, so it was just multiplications. And then you could say, okay, this part here and this part here, and maybe n plus k appears in there. And you could use the factors of 2009, which I don't remember off the top of my head, but I do have a calculator nearby, so I can figure them out. Good thing, by the way, to anytime you're going in to write a Euclid or a Canadian intermediate or senior contest, is to know the factors of the year that you're writing it in, especially if they're good, like if it's a prime, something like that. So it'd be nice if I had a formula, and I guess maybe I could do like this block stuff. I think if I focus on these blocks, there might be a way to get a formula with counting, with the choose notation, with the binomial notations, like the 3 choose 2 and things like that. So you're gonna want to watch the screen, but I'm just trying to think how to explore it to make a string B1, B2, all the way up to Bn. Do I really have to do choices? I think I probably am going to have to do some choices again. I'm not even sure what sort of a formula I could go for, honestly. Because what I'd like to do is say something like, well, as soon as you got a 1, make this sort of a pair. Because then if you can put as many of these together as you want, and you can have as many zeros as you want. But that didn't work up in A, because I had these 10s and then these 0 1s. So, I don't think I can just... And I'm trying to avoid doing a combination of 1, 0, 0, 1 blocks. But could I maybe do... Pick A of the blocks to be 1, 0, and then K minus A of the blocks to be 0, 1s. Unfortunately, they don't have to be put together, and you can have a 1, 0 follow a 0, 1 if there's some zeros in between. So I don't think that'll work out. So, I don't know, maybe I need to prove this recursion and then inductively make a formula for C. Maybe there isn't a fast way to this recursion. But let's see. So B1, B2, B3, B4, keep going. Bn minus 2, Bn minus 1, Bn. Now, if I was going to do this recursion, I'd sort of want to say, well, do I get a string if I chop Bn off? If I get rid of that, if I know that this is, I don't know, an allowed or a permissible, I can't think of a good name. I'm going to call them Rossable, just because that name sort of stuck out at me. I don't know. I'm going to guess it's named for someone like Ross Hansberger or something, but I don't know. So I'm going to call them Rossable strings. Just because I think calling them like allowed is kind of boring. So Rossable. So if I've got a Rossable string and I get rid of the last one, does that mean I have a Rossable n minus 1 string? I don't think so. Because what could I have? I could have a 1 here and a 1 here and a 0 here. And if I get rid of that 0, then suddenly I've sort of got 2 1s side by side when I close this all up to form a loop. So what could I do? Well, I don't want to, but let's see if we can explore with some cases. If Bn is 1, And Bn minus 1 is 0. B1 is 0. So then we've got 0, B2, B3, Bn minus 2, and a 0. And this is also Rossable. By the way, if you're going to use the term Rossable when you do a question like this, define it. I'm just doing this because I've said it verbally that a string that follows their rules, I'm going to call it Rossable. And it has k minus 1 presence, but it's of length n minus 1, so that's not good. But I suppose I can get rid of the 0 here as well. So this is also Rossable because this is Bn minus 1. Like, the problem is when I have gifts, and I remove some of them, there's always the risk that everything in the middle is still fine, but it's now when I join up the two ends, they might be gifts. But I know this one isn't a gift. So I can actually remove the last two, and it's still Rossable. You probably should write that up a bit, but I think that's fine. And it has, well, we've gotten rid of one gift, so k minus 1 presents or gifts. And the length here is n minus 2. So, okay, that's fine. But must the other case be if Bn is 0? Because if it's 0, then I can't just chop off the last one and get a Rossable string. But if it's 0, what could we do? Or maybe this is how I should be counting things. So, if Bn is 1, then I've got 0, some stuff, 0, and Bn. Now any string in here can be made out of blocks that look like 1, 0, and zeros. Right? So, yeah. So let's make that argument that so if Bn equals 1, okay. I don't know if this is going to actually lead to something, but I think I can at least count the number of ways to make a Rossable string that ends with 1. So if Bn equals 1, then B1 equals 0, Bn minus 1 equals 0. And the string B2, B3, B4, all the way up to Bn minus 2, Bn minus 1 can be written as, I'm losing one, so k minus 1 blocks that look like 1, 0. I don't have to use 0, 1s, because if I did use 0, 1s, then Bn minus 1 might be a 1, and that wouldn't be allowed. What if I want B2 to be 1? So I guess this should be a B1, B2. Yeah, because this is guaranteed to be either a 0 because he's a 0 on his own, or part of a 0, 1 system. So, wait, no, because 1 zeros. Never mind. I'm getting... Get rid of this. Get rid of this. Maybe that's the other way to do the other one. So I can... B1 can be... B2 can be a 1, in which case then I have to have 1, 0. Or it could be a 0, in which case who cares what happens next. So, k minus 1 blocks of 1, 0... And then what have I got left? It's n minus 2 of them. Minus 2 times k minus 1 blocks of just 0. Right? Is that... I feel like that's going to work out. Yeah. So that's each k minus 1 block gives you that. And I guess we can simplify this a little bit to n minus 2k, and then minus 2 minus 2 times negative, so minus 2 plus 2, so okay, it's just n minus 2k. So this is n minus 2k, choose... No, it's... Wait, what? It's going to be total number of spots for blocks, so that's going to be the sum of the two of them. Choose k minus 1. And that's going to be n minus k minus 1, choose k minus 1. So there is some binomial thing, a bit of binomial going on here. Fine. But that's just if Bn equals 1. And you may be a bit more comfortable if you wrote a bit more justification here, but I'm going to say clearly any k minus 1 blocks of 1, 0, and any blocks of, or any n minus 2k blocks of 0 will do, and I'm pretty confident that this will break down into 1, 0s, and 0s. But if you want to write a bit more justification, more power to you. Alright, so that's if Bn equals 1. Could I do a similar sort of counting argument for Bn equals 0? So if Bn equals 0, once again, can I think of this in terms of blocks that are 1 zeros or 0 1s? Yeah, because again, our blocks can always end 1 0, because I can have 1 0 and then I can have any number of zeros. But I can't guarantee that any rearrangement of the 0 1s will do, because what if it's the last two? Oh, that wouldn't be allowed. Okay. This can be made this can only be made with any, so let's say, arrangement of, this time I'll have k 1, 0 blocks. Because I don't drop one of the presents, because I don't have it positioned on the nth spot. And then we've got n things to deal with, minus 2k of them, 0 blocks. Really? Again? This can be done... n minus 2k plus k, total number of blocks, and then choose where the 1 zeros go. So here's a formula for fnk. I think this will probably be helpful when we do, so that'll be n minus k. So n minus k minus 1, k minus 1, plus n minus k, choose k. So here's a formula. I would say I've justified this formula. I think it'll be useful when I do C, but I still need to show, like, I haven't proved B yet. I still need to show this property, but now that I'm in binomial territory, I think we're fine. So recall with binomial notation, the thing that I worked out a little while ago. Then n minus k, choose k. But it was n minus k, right? Yeah, n minus k, choose k, and n minus k minus 1, choose k minus 1. Wait, shouldn't that be a plus 1 then? Let's go back and double check. Okay, that's why, because it's minus 2k canceling out with k. That's why it's always a minus k. Okay. Alright, plus n minus k minus 1, choose k minus 1. So this will be n minus k minus 1. Just splitting up this first one. In fact, I think I'll color code it. Because, you know, I have all these colors and I barely ever use them. So that one goes to n minus k minus 1, choose k. Plus n minus k minus 1, k minus 1. Plus. And then this one's n minus k minus 1, k minus 1. And that would break down into n minus k minus 2, k minus 1, plus n minus k minus 2, k minus 2. And then I think if I pair these two up, and I pair these two up, yeah, this one here is f of... So I'm dropping 1, but my k values are the same. So this should be n minus 1 k. And then, so that's where that goes. And then these guys here, I'm dropping a k each time. So where I had k before, now I've got k minus 1s. So this will be f n minus 2 k minus 1. So we're done. That finishes up B. And I've got a formula I can use in C. So that probably wasn't the only way you could do B. You probably could do some of the binary string, what are the last couple, and do some casework. But I think, like, doing binary strings and Fibonacci numbers, I don't think it would lead to a formula. I could be wrong. But I think probably this choose stuff was the easier way to go. How do I actually make strings from scratch versus how do I make strings from smaller strings? That's the difference between the two. If you make strings from smaller strings, smaller Rossable strings, then you're just going to have sort of this recursion, which proves B, but I don't think sets you up very nicely for C, because additions and 2009 multiples aren't going to be the best Although, you know, I could be wrong. Maybe there's a nice pattern, and who's to say I'm going to be able to do C very easily. So, FNK. So I like this formula, but it also has a sum, and I don't like that for multiples. So I want to see if I can play around with this. Now, in the past, usually when I do this, it doesn't go so well for me. I'm thinking of a recent, I want to say it was a Euclid, that I did, or maybe it was a Hypatia, and I just was fumbling around with formulas, and it didn't work out well. Oh, you know what it was? I think it was the 2008 Euclid with that counting triangles thing. I think I messed about with formulas too much there, so I'm feeling a little shy. But okay, let's dive into the world of factorials. And just for a refresher, we've got our formula for binary notation. I wouldn't quote this to anyone. I'm just writing it down for your sake. So n minus k minus 1 factorial. Top number factorial divided by bottom number factorial divided by top number subtract bottom number. Let's be very careful here. Minus k minus 1 factorial. K minus 1 factorial. N minus k minus another k, so that'll be n minus 2k. And then minus 1 minus another minus 1. I think we're good to go. So we've got n minus 2k's for both of them. Now I could take out a factor of k here and get k minus 1 factorial, but I think the safer thing to do would be to multiply top and bottom of the second one by k. So k and then n minus k minus 1 factorial. And I can put a k down here, and k times k minus 1 factorial combines to be k factorial. If you're confused by that, stop watching Euclid 10s and start learning more about factorials, because it's a far more basic thing to be able to manipulate comfortably. Okay, Euclid 10s are sort of the peak. You have to know a lot of math. Okay, so I got these, and now I can add this a little bit. Not only that, I've got a factorial up here that I could mess with. I think, yeah, now that I've got, I think I can get rid of this plus sign. It might be a bit messy, but I think I can get rid of this plus sign. So n minus k minus 1 factorial plus k n minus k minus 1 factorial all over k factorial n minus 2k factorial. This might even be a cleaner formula. I wonder if there's a quick way to... Okay, n minus k plus k is just n. And we've got k factorial n minus 2k factorial. Now, it's interesting that we have a k stuck outside here, and we technically had a k out there as well. I don't think this is going to help, but n minus 2k. This is n minus k minus 1. Choose k minus 1. So that's a formula. I don't know if that one's better or worse. I mean, they're basically the same thing, but yeah. Yeah, so that's interesting. And I think maybe if I'd noticed that there might be an interesting way to get that. I think with the n over k, because that's not guaranteed to be integer, I don't think there's a clean way to get this formula here from binary strings, but it's still an interesting formula. And it seems like it should be a common formula for other things. Now, both this one here and this one above it are a bit messy. This one here is just sort of an intermediate stage. I think we could clean it up a bit more as well. Cancel out some things. Fnk is going to be... n sort of stays where he is, but then we do n minus k minus 1, n minus k minus 2, now n minus k minus 2k plus 1, and then it'll cancel out with the bottom. N minus 2k factorial. Oh dear. And then k factorial n minus 2k factorial, and now that cancels. And so I guess I've got n minus k minus 1, which is a bit of an odd jump. But it's a little nicer to work with, k factorial. I guess, for stylistic reasons, maybe we'll k minus 1, k minus 2, all the way down to, well, it's 1, actually. Okay, so I think that's probably the smallest I can make this formula and still have it be effective. But I like this. I like this a lot better than the sums and the recursion formula we had in B, because this is multiples, this is division, this is factors. This is Factor City, and if I want to talk about multiples of 2009, this is the sort of thing I need to be working with. Okay? So, if we want multiples of 2009, parts of the bottom will cancel out with parts of the top. You will always get an integer. I can guarantee that, because our formula was not based off of something we plucked out of thin air. It was based off the plate problem. And since the plate problem will always have an integer number of answers, this will always be an integer. So the k factorial on the bottom will cancel out with parts of the top. And I need to just make sure that when the dust settles, there's the factors of 2009 are still up there. Plus some other stuff. I don't care about the other stuff. Now, I'm a little upset that there's no n plus k anywhere in here, so I don't think there's going to be a quick answer. I fear that there might be some casework. And I don't want to do case. It's been a long problem already. I don't want to do more casework. I tend to get bogged down in casework because I never see the... I always find when I read their solutions jump right to the correct cases, which of course is correct. And it's a criticism of my videos that I fumble around for half an hour, but I never see the right cases right away. Anyway, it's high time we figured out the factors of 2009. Not divisible by 3, not divisible by 5, maybe divisible by 7. I don't know. I'm going to grab my calculator. Calculators, of course, allowed on the Euclid. It is divisible by 7. So 7 times 287. It'd be really interesting if 287 was a prime. Not divisible by 3, not divisible by 5. Could it be divisible by 7 again? Oh, you know what it is. And so I got 7 times 7, or 7 squared times 41, and I know 41 is a prime. Now 41's a pretty big number, so I think it's a bigger number, so I think it's a good place to sort of attack first. So could I have something like n is 41? Because n's got to be bigger than k, otherwise terms like this otherwise the problem isn't defined. There's no way I could put 6 gifts out if there's only 5 plates. So n's definitely, n's got to be bigger than twice k, even. N has to be at least twice k. Okay, so if I had n is 41, nothing in the bottom would cancel out that 41. And then I just need to make sure I get 2 7s up on top. So I could have n is 41, and then I start with n minus k minus 1, and how many terms do I have here? K minus 1, 1, 2, 3. I've got k minus 1 terms here. So to get two factors of 7, because I'm not going to run into a 49 amongst these, because 49 is bigger than 41, I would need k minus 1 to be at least 8. At least 8, because then, maybe this one could be a multiple of 7, and this one could be a multiple of 7. But then I'd have at least one multiple of 7 down here. And that would cancel out. So then I'd need k minus 1 to be... You know what? No, because I can't... I'm not going to get extra factors of 7, I think. Yeah, I don't think I'm going to get extra factors of 7 lying around. I need 2 factors of 7, but by the time I reach... the first one could be a factor of 7, maybe the second one, I don't know. But by the time I reach my next factor of 7, there will be enough terms down here to have a factor of 7 to cancel it out. So I sort of need... I can coax 1 out of here. But the second one is going to be a problem. So maybe I don't focus on 41. Should I be focusing 47? What if n is 49? That would get my double factors of 7 out of the way, and then maybe I'm lucky enough to get a 41 lying around. 41 in this particular range, the k values are still going to be so small that none of them will have a 41, so we'll be fine there. So, okay, try n is 49. That gets my double factor, so 49, and then I need to go a little further down. I'll get some number, and a 41 somewhere in here. Could be the first one, could be the last one. N minus k minus 1. N minus k minus 2. N minus 2k plus 1. I just need to find a 41 up here, and that would at least be one situation that works. So, if k is 1, we're not going very far here. K is 1, we get 49 times 47, and there's k minus 1 here. So we actually have to have k at least 2. So if k is 2, I'll get 46. That's a little too big. How about k is 4? If this works, then I can also check k is 3. So we'll get, subtract off 5 there, so we'll get 44, 43. So we'll get, we'll need 3 terms here, so 42. So we just miss it. How about 5? So that'll be 43 times 42 times 41 times 40. 4 won't work. 5 will work. We'll just double check. So what am I dividing by? 5, 4, 3, 2, 1. Yeah, no factors of 7. So I'll get my factors of 7 here. I'll get my 41. And everything cancels out. There's 40, and then you'll get a 14 here, but no one cares. So F49.5 is a multiple of 2009. Now we want the smallest one, but they sort of have they want n plus k. Okay, n plus k to be as small as possible. Well, I suspect that the closer the numbers are together, the smaller the sum will be, but this has n plus k is 54. That's going to be hard to beat, but I think if I make some sort of argument that you have to have the 49 on top, then that'll force the 49 to be n, just to be smallest, I think. And then, yeah. I think that should do the trick. Okay. And since that's sort of the way I figured out the 4950, I'd be surprised if there were a smaller one, but we'll find out. I'll start off by saying we claim 54 is the smallest. sum. Okay. What could I do? So focus on the double sevens there. So to be a multiple of 2009, we need an extra factor of 41 on top and 2 extra factors of 7. But they don't all have to come from the same place, but I'm going to argue that they need to be 49. Okay, maybe n could be a multiple of 7. What if I had something like 40? No, 42 would miss 41 because it jumps a fair bit from n to the n minus k minus 1. Maybe there is something smaller than 54. Maybe 54 is a nice, easy one to find, but maybe there's a nuanced argument that there's a smaller one. What could I do? What could I do? I'm not sure how to make this argument. Maybe it doesn't have to be 7s, but 7 seems the most likely thing to do. It seems like it has to work out. I'm just trying to think of a good way to phrase this and pick a decent starting point. I don't know. Maybe let's entertain the notion of 41 for a moment. It didn't go well for us, but maybe. So 1 of n minus k minus 1, n minus k minus 2. I mean, the 41 at least is nice because he's all together. The 7s could be spread out, and that's what I just realized. N minus 2k plus 1. Must be a multiple of 41. I think it's pretty safe to say that it has to actually be 41. So if this factor is not 41, it is at least 82, and then it follows that n is at least 82. Because this could be 82, or one of the smaller ones could be 82. So n plus k is at least 82, and so that at least is more than my 54. Let's say greater than 54. So it must be 41. Okay, must be 41. And here's where I'm going to have to do cases. I don't think n can be 41, but I should probably explain that. Alright, if n is 41, then n minus k minus 1, n minus k minus 2, all the way down to n minus 2k plus 1 are less than 49. So we need two more multiples of 7 on top than we have on the bottom. We've got k consecutive numbers on bottom. If our n plus k is less than 54, then k, so since n is 41, then that means k is less than 13. So only one factor of 7 on bottom. But even 13 consecutive numbers only have at most two multiples of 7. So since the factors on top are less than 49, and we have at most two factors of 7 in total for top, which is not good. So that won't work. So 41 is right out. All right. If n is greater than 41, then it's got to be one of those other factors. K is at least 2. So n plus k has got to be greater than 43, but it's got to be less than 54. I'm not exactly seeing this being helpful, but at bare minimum, so k has got to be less than 13. Guaranteed less than 13. If it were equal to 13, since n is bigger than 41, then we'd have something that's equal to 54, and we've already done that case, so don't worry about that. So once again, we have at most let's say this. So I want to do the same sort of thing, but if n equals 49, we've seen 5 equals k is smallest. Suppose n is greater than 49. I'll come back to n less than 49, but suppose n is greater than 49. Then then n plus k has got to be greater than 49 as well. Actually, it's got to be greater than 51. So k is less than 5. So k could be 2, 3, or 4. But for n equal to 50 and k equal to 4, you'll get 50 times, you do k minus 1, so you get 50, 45, 44, and 43 k minus 1 terms here, which has no 41. Even with 51 and k equal to 3, you still get 47, 46. You still get no 41. And with n equals 52 and k equals 2, and that's the smallest I can make k, we get 49, 48. It has no 41. And incidentally, these two here don't even have 49 kicking around. So n must be less than 49. Well, less than or equal to 49. I know the 49 and 5 case works, but now let's say if n is less than 49, n is greater than 41, and k greater than or equal to 2, and then if n plus k is less than 54, which must be greater than 43, then k is no bigger than 13. So we have at most one factor of 7 on the bottom. With n less than 49, n minus k minus 1, n minus k minus 2, and n minus 2k plus 1, also less than 49. And once again, at most, 2 factors of 7 for the top. So we don't get a surplus of 2 factors of 7. Therefore, n equals 49, k equals 5, n plus k equals 54 is the smallest. Okay, let's briefly go back. I think we've got it, but let's briefly go back and run down our argument just to make sure we haven't missed any cases. Don't want to miss cases at this point. Okay, so 54 is the smallest sum. We figured out 54 works pretty quickly. Focusing on factors of 7, and it looks like most of this proof has been focusing on factors of 7. So let's see if we can get smaller. So we know we have to have a 41 on top. If it's anything other than just the factor 41, it'll be too big. Okay. So we know we definitely have to have a 41 on top. It could be either n is 41 or 41 is one of the other factors. Well, if n is 41, the other factors are less than 49. So if they're multiples of 7, they only bring one factor of 7 to the table. There's at most 13 of them. And so 13 consecutive numbers. If you're going to have 2 multiples of 7 in a set of consecutive numbers, if you're going to have 3, you need at least 15 numbers. Right? Yeah, at least 15 numbers are required. But we have less than 13. You would probably want to mention that 15 is the least you need. So they're all just multiples of 7. They only bring one factor of 7. So there's at most 2 factors of 7 on top, because we can't get to that precious 49 that has double factors of 7. I suppose... I said so only one factor. I mean, at most, one factor of 7 on the bottom. I suppose we could have 0 factors of 7 on the bottom, but then you wouldn't... So I guess this needs to be an extra case. I'm just going to throw this in at the end and clarify it. So this is a clarification that I should probably... I would erase and add, but I've done so many pages already. So if there are k less than 8, if k is less than 8, then and. So anytime we have this situation, which happened, I think, twice in our proof. So actually k has to be less than 6. No factors of 7 on bottom. But k minus 1, which is less than 5, consecutive terms, n minus k minus 1, n minus k minus 2, n minus 2k plus 1, have at most one multiple of 7, and therefore one factor of 7. If k is greater than or equal to 7 and less than 13, then one factor of 7 on bottom, and at most 2 factors of 7 on top. Either way, no surplus of 2 factors of 7. Let's say don't have 2 extra factors of 7. Okay, so that clarifies that thought, but let's continue proofreading and then we can be all done with this one. Okay, where were we? Okay, so there we go. That finishes that off. Anytime it's less than 49. So that happened if n was 41. Now, if n is bigger than 41, if it's 49, we're good to go. If n is bigger than 49, we've got a bit of a problem. If n is less than 49 and n is greater than 41, oh, could we have 42? No, you can't have 42 because then you wouldn't get a 41. So that's something else I need to add. I'll just press the plus button. If n equals 42, then k being at least 2 means that we do 42 times means that n minus k minus 1 is at most, it's at most you subtract off 3, so at most 39, which is less than 41. So we get no factor of 41. So that's something I was missing. Because that could have given us a factor of 7, and then we'd have that extra surplus factor of 7. But there's all kinds of mess here, but I think we're making progress. So that's something. And then in the other case, we again can do this counting factors of 7 argument. And that does, in fact, finish things off with these 2 additional notes. If I hadn't added them in, I don't know, I probably would have gotten 2 out of 4 for that one. I'm not entirely sure of the marking scheme. This is before I was down marking these things, but I think that finishes things off. It was a little long one. I think this might be over an hour. I don't know. But that finishes off question number 10, and that's going to finish off the whole Euclid for us. So that's Euclid 2009 for us. Next Euclid will be Euclid 2010. But of course, I'll be going through other 2010 contests and a couple other things in between. So stay tuned for that. And yeah, whatever video you watch next, thank you for watching, and I'll see you there.